Okay, so in the same style as the previous definition, I'm going to try and solve the sum of this bigger list in terms of the sum of this slightly smaller list. So you have to ask yourself, what do I do to this smaller list to get the sum for the slightly bigger list? So this is a sum for the rest of the elements where we've ignored this first element. So what do we do with this to get this? Well, we need to take this one element and we need to add it in to the sum of the rest. So it's going to be n plus the sum of the rest of the list. Okay? And let me just put primes on that again because I keep forgetting. Otherwise it will get all very confused. Okay, so what about the types? So it's going to take a list of things as arguments. So what about this type? List of int, and we get back an int. How does that look? Well, is that a correct program? So the answer, the question is it a correct program?
Yes.
These guys like it. Let's just compile it. It's a correct program. But if I define the type like this, what happens if I want to do the sum prime of 0.1 and pi, for example? Doesn't work. But what if I use the built-in sum function for 0.1 and pi? That works perfectly fine. So this type is okay, but I don't want to make like 10 different copies of this function. One for int, and one for float, and one for double, and one for integer. So how do I do it? Yeah. Type classes. We talked a little bit about it last time, but the first step is to say, well, we kind of want it not just to work for int or an integer, but we want to work for all of those things. So we might put a type variable in here. Let's call it a. You take a list of a's and you add them all together to get a single a. So what's wrong with this type? Yes. There's so what would go wrong? Yeah, so
base case.
Yeah, 0. Yeah, so if I chose a list of bool, would this work? Well, it would be difficult because 0 is not a bool, and we don't know how to add bools together. So it doesn't work for every type. So it kind of works for some of the types. Which types does it work for? It works for all the kinds of numbers. So all the kinds of numbers, fortunately, they live in what's called a type class. So all the types that have the arithmetic operations live in a gang called num, okay? And that's a type class. So this is roughly the right type, but we must put a constraint. We say, yes, it is this type as long as A is in the num gang, okay? And the way we write that is to write a type constraint on the front of this type. We say that if num A, then this is the type. So this is like saying for all types of numbers, this is a function that takes a list of those numbers and gives you back a number. So this guy is called a type class, and int, integer, floats, doubles, and a bunch of other things are all in that gang. What does it mean to be in the gang? You can add them together. 0 makes sense for them. 0 can be an int, or it can be an integer, a float. So all the pieces make sense for that type. Let's just compile that. And so if we ask what is the type of the standard function sum, we see that it's almost the same. Oh no, it's even more general. So we're not going to go into the details of this foldable thing, but this is another gang. What it's actually saying is it doesn't just work for lists. It works for any sort of shaped structure that allows you to where you can combine all the elements together. I'm going to ignore that for now because I think this is a bit too fancy. You can read about that if you like. So this is actually even more general than my version of sum. But for now, I would like you to think of this sum function as having this understandable, little bit more complicated type. In fact, its Haskell type is even more general than this one, but we won't be needing that generality in this course. Questions? All right. Let's take another couple of examples. Init and last. So these are all functions defined in the prelude. I'm imagining you can guess what last will do. It gives you the last element of the list. So the type of last takes a list of things and gives you back a thing. Okay? And there's another guy called init, which gives you the first part of the list. And these are both partial functions, so they're not things that we're going to use too frequently because they're a little bit dangerous. You have to be careful. And that's because if you take the last of an empty list, you get an error. And if you take the init of an empty list, you also get an error. So in order to use them safely for programming, we need to be sure that the lists we apply them to are not empty. Because if we get an error, then it's game over. Okay, so let's define them. Now, these are operations that kind of do their interesting stuff right down, way down at the end of a list. And that means in order to get there, we're going to have to kind of walk down the list. In other words, we're going to have to use recursion to define these functions. So let's start by defining the easier of the two, I think, slightly easier, last. So the pattern we've been using so far is to write down the base case and write down the recursive case in terms of the ... Okay, that's the pattern we've been using so far. I want to add to that pattern. I'm going to start by actually defining a type. It takes a list of any things and gives you back a slightly shorter list with the last element missing. Ah, last, yeah, you're right. It gives you an element, the last element. Yeah, I'm thinking of a init. Thank you very much. Okay, a list of things and we're going to return the last of them. So whatever the type of the things are, we're going to get a thing back. If we don't get a thing back, it's because we've had an error. So what's the base case? What's the last element of the empty list? Yeah, there is no last element. In fact, this is the error case. So this is actually not the base case. This is the case where it goes wrong. So we could either ignore this case in the definition, or we could give an error message. But the point is, it's not the base case. It's not the simplest case. It's an error case. So what is the simplest case? What is the base case for the last function? It's, thank you very much at the front, it's a list where there's only one element. So I mentioned that the base case, we make it as simple as possible, but we can't make it any simpler than that. And in this case, the simplest possible case for the last function is a function is not the case with an empty list, it's a case with a list with one element in it. So how do we write that as a pattern? Well, we can do it in multiple ways. Let me start by writing it this way. So now we've defined the pattern where this matches any list whose first element is x and where the rest of the list is empty. So this only matches against lists with one thing in it, and that thing will be called X. So in that case, what is the answer? What is the last element of a list with one thing in it? It's the thing. And what's the thing called? It's called X. So that's the base case. Now you remember that when we write notation like 1 on the front of the empty list, that's not the way it's printed. The way it's printed is square brackets with the 1 inside it. And that shorthand, or that nice notation, can also be used in pattern matching because they're the same thing. So we wouldn't typically write it in this way. We would typically write, and we don't need brackets then, because it's already got its own brackets. We would typically write that as the base case. And what is the recursive case? If I want to compute, okay, so what does this mean now? It means that if you give it the empty list, it gives you an error. If you give it a list with one thing in it, that thing is the answer. And now this case will correspond to the case when neither of these two cases matches. So now we know we have a list, X's, which is not empty. Otherwise, it would match this case. So we want to compute the last element of this, where we know that this guy in the front is not the last element. What do? Well, we throw that one away and compute last of the rest of the list. We're trying to compute the last element of 1, 2, 3. We throw the 1 away and compute the last of 2, 3. Okay? So the ... here is, in fact, nothing at all. The last element of this bigger list is just the last element of this slightly smaller list. And we keep going until we get down to the very last element, when there's only one element left, and of course that's the answer. So that's our version of last. Any questions? Okay, 1 minute over. Yes, question? It's not important to include the empty list. Let me show you what happens if we don't. We take the last prime of the empty list, we get an error, and we get my error message. Okay, that might be helpful to you, but it doesn't really matter. The program has gone wrong, so it really doesn't matter which error message you have. If I comment out this line, recompile, and run that again, now I get a slightly different error message, which says non-exhaustive patterns in function last. So this is not important when you run it, but it may be important when you read the code, and it may be important when you suddenly get an error and you're trying to work out where the error came from. Thank you for a great question. Let's take a break. Okay, welcome back. So we looked at the function last. Let's just look at the brother function init. So init was something which takes the initial chunk of a list, ignoring the last element. So kind of similar. Take a list of things, and this is the one where you get back a list of things. And the init, we're going to have the same case. The init also, the empty list is the error case. So the base case is the non-error case. So the initial part of a list with one element is what? Yeah, that element is the last element, and the init function ignores the last element. And so if you ignore the last element in a one-element list, there's nothing else other than the empty list. So the initial part of a list with one element is the empty list. And the initial, let me just call it an init prime as I promised. And the recursive case is the case when the rest of the list is non-empty, which must be the case if we write this equation second. And it's very similar to last. We just compute the init, the initial part of the rest of the list. Now, both of these definitions, we can actually write the patterns in a little bit more informative way. The definitions are fine, but we can actually make it clear. When I say fine, I mean almost fine. We can make this slightly clearer that when we're computing the last element of a list which is bigger than 1, we don't care what the first element is. We're throwing it away. Similarly, when we're computing, oh, this init doesn't look quite right. I guess I should test this function, shouldn't I? So init of the list from 1 to 10 gives us all the element except for the last one. Init prime of 1 to 10. Oops, that gives us the empty list. What did I do wrong here? Yeah, so if we want the initial part of a list and the list is not empty, what do we do with this first guy? Well, that's actually part of the initial elements of the list, because we know that this is not the last guy, so it must be part of the result. So we need to put this X on the front of the rest of the list.